I want to do two things today. The first, I'm going to sort of wrap up a few miscellaneous vector stuff. And then we're going to go through a three-part detailed example of an abstract two-dimensional vector space that will then prepare us for all the stuff we're going to do later. Now, the one thing we closed with in the last segment that I just want to quickly re-emphasize is the idea of scalar product and how it's often defined. So if you recall, we came up with an example of a two-dimensional linear vector space, which was linear functions, and we let x be one of our basis vectors, which we might call x or basis vector 2. And 1 was our other basis vector. And this is where the ket notation becomes very useful. We can label the ket very nicely based on the basis vector we want, 1 or x. Now, having done that, we have to ask ourselves, what do we want for a scalar product? And we already said multiplication doesn't work because multiplication doesn't give us a scalar. In fact, it gives us a quadratic function. So this does not work for the scalar product. And in fact, we don't really have a good geometric idea, but we can say, well, let's make our basis orthogonal. In fact, let's make it orthonormal. Hence, the value of labeling things by 1 and 2, I can say, and I just declare, the scalar product to be defined by the fact that ij equals delta ij for ij equal 1 and 2 for our basis vectors. And once you define the scalar product for one set of basis vectors, if you find another basis as a linear combination of your original basis, you're done. You know how to do it for any set of vectors. And the reason we know how to do it for any are because of the way the scalar product is defined. So if I now take f of x, which I can write as a1 plus b2, and I take g of x, which I write as c1 plus d2, I can now compute the scalar product of f and g. Well, f as a bra is just a1 plus b2. Notice if a and b were complex numbers, something to keep in mind, I would have to take the complex conjugate here, because that's what it means to turn it into a bra. And I'm going to multiply that by c1 plus d2. And I get a times c, 1, 1, plus a times d, 1, 2, plus b times c, 2, 1, plus b times d, 2, 2. And what does that big long expression equal? Anyone? Okay, why does it equal AC plus BD? Because of my definition. I've defined how the basis vectors scalar products work, and I've defined them to be orthogonal. So 1, 1 is 1. They're not only orthogonal, they're orthonormal. I defined them to have unit magnitude. 1, 2 is 0. 2, 1 is, and 2, 2 is 1. Notice, to be a basis, I didn't have to make them orthogonal. I could have defined a different scalar product, right, where 1, 1 was 6, 1, 2 was 3, 2, 1 was -1, and 2, 2 was 5. And I would still know how to compute this scalar product. It would be a weird definition of it. It would not be orthonormal, but it would still work. I'm free to do that. And that's why there's a certain arbitrariness in this particular case. However, if you notice, it does kind of give you what you might want for getting out the scalar, right? The natural thing might be to take the A and the C and multiply each other, and the B and D multiply each other. That looks just like the dot product for geometric vectors when we write it in components. And that's why in geometric vectors the dot product works out the way it does. It's because we're using orthogonal basis, x and y, and you don't get cross terms. Now, I want to emphasize that because it's very useful for when we're trying to consider different bases. So if I have, in this case, made this analogy, or not this analogy, this identification, and I can now also go to column vectors if I so wished, I can consider two new functions. F of x equals 1 over the root 2, 1 plus x, and g of x equals 1 over root 2, 1 minus x. Perfectly fine functions. I might call this, in terms of a cat plus and this minus, it's a convention that we use a lot. Why? Because I added the two basis vectors and I subtracted the two. So you'll see that it'll be common. Now, let me ask you this. Quickly, on your own or with a neighbor on paper, answer the question, are these two vectors forming an orthonormal basis themselves or not? So for this vector space, with these two basis vectors where we still have the dot product defined that way, are these new vectors, the plus and minus, an orthonormal basis or not? Since I don't see a lot of writing, I'm going to assume we're fairly confused. How would I even start to answer this question? Well, let me ask you this. What does it mean for it to be an orthonormal basis? What four multiplications should I check? What four scalar products do I want to check?
A, C, A, D.
No, I'm talking about these.
The plus.
I want to know plus. What does plus plus have to equal?
1.
1. What does minus minus have to equal?
1.
And what does plus minus, which, since we're dealing with real numbers, we know by definition equals minus plus. What does that have to equal? 0. So what three multiplications do I need to check? Those. Very good. Okay. Now, so so it's critical. One of the things that you really, as we do these more abstract things, you want to keep in mind, definitions really matter. One of the things that causes people the most trouble as they make the transition from lower division to upper division physics is lower division physics, you were able to solve problems and do things without really knowing why you were doing it. I hate to say this, the reason you've made it this far as a physics major most likely is you're too smart to know what you were doing. You just did lower division physics because it made sense and it was intuitive to you. As you get to upper division physics, it is almost impossible. Now, some of you will get through upper division physics still not knowing what you're doing just by doing it. Some of you, right, some of you will get through the junior year that way. And some of you will get through half of the junior year. But at some point, you have to just apply physics is a set of hard and fast rules that you just apply, whether you understand them or not. I've given you the definition of orthonormal. Even if you don't know what it really means, you can still apply it. And part of learning physics is you apply the rules enough, then you kind of intuit them and they become part of your intuition and you understand them. It's a weird thing to learn. You can do physics before you understand it if you pay attention to the rules. And it's really important to be willing to apply rules you don't understand to make progress in physics so that you can then reach the understanding. It's just a strange way of learning it. So I've asked you orthonormal, so you need to do that. Now, since we're working in bras and cats, that means I need to know how to translate plus into bras and cats. Well, it's this function, which I realize is just root 1 times my first basis vector times 1 over root 2 times my second basis vector, and minus is 1 over root 2, 1 minus 1 over root 2, 2. And we notice, I'm going to let you do the details of plus plus. So if I multiply plus with itself, okay, I'm going to get terms like 1, 1, which will be 1, 1, 2, which will be 0, 2, 1, which will be 0, and 2, 2. So I'm going to have two terms left that are 1s from the scalar products that are 1 over root 2's times themselves, which become 1/2. So I'll get 1/2 plus 1/2, so plus plus will be 1. Minus minus works out the same because this minus sign becomes a plus sign when I do 2 times itself. So those two you should check. And I'll just do, so you have one example to build on. If we want to do plus minus, everything has a 1 over root 2 for the plus. So that's 1 plus 2. And it's times the 1 over root 2 times 1 minus 2. So I'm going to get a 1/2. And I'm going to get 1, 1 plus 2, 1 minus 1, 2 minus 2, 2. And notice those are both 0 because they're 2, 1. And this is 1/2, 1 minus 1, the 1 from there and the 1 from there, which is 0. So indeed, they're orthogonal like they're supposed to be. So I constructed another orthonormal basis. And I could go and construct more. Because remember, in the plane, we said there was actually that infinite number of pairs that are orthogonal. Any questions on that? The final idea I just want to mention is, just so you're aware of them, we will occasionally talk about a subspace. That's easiest to see just quickly with an example. If I take these two vectors, they clearly form a two-dimensional subspace of 3D space, right? That 1, 0, 0, 1 span the space of all things with components only in the top two places, and any vector with a 0 in the bottom. Right? If I try and add any other vector with a 0 in the bottom, any a, b, 0, this will not be linearly independent. So that's an obvious trivial case of because you can just look at the components and see that it was a 2D subspace. Sometimes it's more subtle, right? There might be a 2D subspace that's a plane that's sitting through all three of your axes. And so you might have two vectors that span another 2D subspace, right? Any plane in 3D space is by definition a 2D subspace. And they're not all as trivially obvious. But sometimes in physics we're interested in the subspace. And the reason is because often you have an operator, like say this one, what do you think that operator does? Nah, it doesn't reflect. Rotates where?
On some plane or?
Yeah, so if I call this the x, y, and the z-axis, what is it doing to the z-axis?
Keeping it the same.
Keeping it the same. So it's rotating. Notice it only, any vector in the subspace stays in the subspace. Right? A vector that's a mixture has something weird happen to it. But it preserves the subspace. So we would say, you know, rotations under this matrix in the subspace are preserved, so it acts just on the subspace. So, and that's sometimes of interest.